at the Institute of Mechanics, ETH Zurich. He has developed substantial IP in the field of fluid property sensors with 11 granted patents and more than 20 pending. He has a Bachelor's of Science and Engineering in Aerospace and Mechanical Engineering Science from Princeton University, a Master's of Science in Biomechanics from Stanford University, and a Doctorate of Technical Science from ETH Zurich in Biomechanics. Early in Joe's career, he worked with SRI, Stanford Research Institute, then and thereafter headed the IMES labs at ETH Zurich. Joe is also a trained psychotherapist and a founder of, I think I gotta move my head, of the Institute of Process Work. He is an author of 4 books on the subject. So with that, Joe, I'm gonna go ahead and turn it over to you if you wanna pop on your camera and unmute yourself and go ahead and steal the screen away from me, Joe. It's all yours.
Okay. Yes. Okay. And one more. Yes. Okay. Technology rules. Great.
There you go.
Thank you very much,
Joe. It's all yours.
Okay. Thank you. So I'd like to thank Joe and Mark Sisternino, along with the everybody at the FTA who made this possible. And we're very, very proud to have been awarded the FTA Technical Innovation Award for 2021. It's been a real pleasure working with you folks all along. I want to say that along with me today is our good friend and accomplice, Bert Verweil, who is a flexographic printer in Rotterdam in the Netherlands. And Bert will be a panelist. He'll help with answering some of your more pointed questions about flexography. And Bert was instrumental in the development of the technology that I'm going to be presenting today, and was an early adopter. And he also has written this article that you see on the left here, the first article we've published about our viscosity measurement and control systems. Okay, so I want to start off with a poll question. And if I say the term viscosity control, what's the first thing that comes to mind? It could be, what a mess, I'd prefer to avoid this if possible, or I have to do it, but I'm not sure what the benefits are, or this ink needs to be adjusted to the cup second value on the spec sheet, or lastly, it's a powerful tool for optimizing color quality. So I'm going to go ahead, while you're answering that, I'm going to go ahead with the presentation. And first of all, we're aware that hitting color accuracy targets is one of the central technical challenges in flexographic printing. And there's a lot of really, really amazing technology that goes into these high-speed presses. The first time I saw one, I was just amazed. And yet, in spite of that, somehow viscosity measurement and control has not kept pace with the technology that supports this amazing process. So, of course, we all know that clean, accurate viscosity measurement is central to maintaining color quality, and that's the goal of this product that we're going to be showing you today, is to bring viscosity measurement for flexography up to the standard of the rest of the technology. So, first of all, this is a roadmap of what we're going to be discussing here. So the first, we're going to concentrate a bit on how is viscosity related to color excellence. And we're going to discuss how it is that excellence can be achieved by tighter viscosity control, and how the Rheonics InkSight system enables that, how it makes it possible. Then we're going to move on to talking about the InkSight system itself and talk about how what I think is the first in the industry that we can actually print to DE 2000 by freeing the operator from viscosity measurement. The direct goal is, if you want to keep up how do you translate a spectrophotometer reading into concrete actions that are going to help you keep the color, first of all, correct at job setup and then on the beam during the whole run. And then finally, we're going to show you a case study that was done at Bert's shop in Rotterdam on how the InkSight contributes to actual quality and actual better economy and of solvent use and other such things during the last part of the presentation. So first of all, let's talk about viscosity and color excellence. First of all, it adds value. I know that one possibility when you're printing is you say, okay, this is our DE 2000 level that we're trying to reach. That's what the customer demanded. And yet what happens then is you cultivate a culture where the customer is looking to do things for the cheapest price and you become a commodity. But we know also that brand identity is becoming more and more important, and color forms an integral part of brand identity. When you think about a Coca-Cola red or a Heineken's green, if it doesn't look right, the customer moves on, or even thinks, what is this stuff? I mean, it doesn't look like what I'm accustomed to. So acceptance of jobs depends very much on high color quality. And the better the quality, the better off you are in being able to get return business and forging a real link to customers who trust your ability to deliver what they want. And so there are two aspects of that. One is hitting the color right at the beginning when you're setting up a job. And another is how do you maintain that constancy of quality throughout a whole job of like 24 kilometers of material. So here's a second poll question. In your experience, how does ink viscosity affect color density? So one possibility is, well, the thicker the better. You put on more ink, the color density improves. It doesn't matter as long as my DE 2000 values are below 2 or whatever the job spec is, I'm satisfied. Or I honestly don't know. We mix our inks according to the recipe and usually it works out just fine. Or possibly we're still not sure about that. We tried some experiments, but we could never get the same measurements twice. Remember, viscosity cups. So we're still sort of in the dark. Or finally, there's an optimum viscosity for each ink, but we had to determine it by experiment. And again, Joe's going to give you a chance to stay with the questions for a while. I'm going to move on to the next bit of the presentation. So first of all, what can tight viscosity control do for color excellence? So here's an experiment that Bert did in his shop, where he took some ink and started off with high viscosity, low dilution, and progressively diluted the ink and took test prints, measured the viscosity of the ink, and also measured the deviation from the optimal point. And as we see in the graphic over here, it turns out that at about 46 or 47 centipoise, he got a DE 2000 value relative to the master of very close to 0. And as the viscosity was further diluted, then of course the ink density, the color density decreased. But if you look on the side of higher viscosity, interestingly enough, the DE2000 value also increases, meaning that the color density is decreasing. And the reason for that is that when you put too much ink on the substrate, you begin to develop pinholes, so the overall color density decreases, despite the intuition that putting more ink on the paper should increase the color density. So where are the points in the process where tight viscosity control can be useful? The first one is in job setup. And there you're trying to hit a target of initial color quality, initial proper density for each color. And then you want to be sure that you can hold that through the entire run. So the more accurate you are at the beginning, the less correction you have to do as the run progresses, and the better chance you have of keeping that color consistent during the whole run. Now, one of the two of the things that stand in the way of keeping color constant, one is that most measurements are offline, which means that, for instance, if you're taking samples of ink and measuring the viscosity with a cup, it's a slow process, and what's actually happening in the press is not quite the same thing as what's happening in your cup. But then perhaps the second, maybe a more difficult problem, is that strangely enough, a lot of the more advanced viscosity measurement and control systems still refer to cups for calibration. So any system that requires repeated calibration is going to unfortunately be subject to the same kinds of variations that you found in the cups. So there are several different ways in which viscosity control supports excellence. So the first one we talked about was accelerating job setup, because you can hit the target very quickly if you have accurate measurement and viscosity control. You have to do less trial and error adjustments, and the amount of scrap is lower. Another is, again, as we were saying, maintaining accuracy throughout the run, which means that if you can control the viscosity, keep it on the target that you set during setup, then the chances are much better that you can keep this consistent quality, and you'll get much less waste and job material rejection by your customers. Then, of course, there's the issue of improving customer satisfaction. If customers see that your color really pops and it really corresponds to what they're looking for, then the chance of getting repeat jobs is much better. And finally, as we'll show at the end, if you can keep viscosity on the nose and not have to do too many dilutions and corrections, it's actually more economical, because it reduces the solvent consumption and allows you to work with smaller amounts of ink in the bucket. And overall, it's more economical and has lower environmental impact. So here's poll question number 3. How often does viscosity actually have to be measured and corrected during a print run? So first possibility is, well, I'm not sure. We have an automatic system, but we don't know really how often it measures and corrects. The display shows swings of a couple of cup seconds, and that seems to work for us. Second possibility is we do it with cups. We do it about once every 15 minutes. And that's really all we can manage, because operators also have to be running the presses, and they can't always interrupt the workflow to tend to the ink. And that's especially true when we're running 8 colors on 5 presses. Or possibly we measure it once when we mix our ink recipe. That seems to hold, or almost never. Our control system is so accurate, we can just set it and forget it. Okay, so go ahead and answer that, and Joe's going to collect the answers, and I'm going to, again, move on. So, what was our motivation for getting involved in the printing business, especially in the flexographic business? We've been in the viscosity business, including my earlier experience at the Swiss Polytechnic, the ETH. We've been in this business for close to 40 years. And we've been involved in a great number of different industries. And printing has always been one of the things that's interested us. And we actually had in previous incarnations had some impact on the flexographic business. But we also learned through that is that these ink control systems have come and gone, that some of them have proven unreliable for one reason or another, or too complicated to run. So that gave us the impulse to really study the problem and talk to people in the business and find out what operators really were looking for and what would keep them using the device instead of putting it on the shelf and saying, well, that was an interesting experiment, but really it was too much trouble. But I think that the biggest thing that we learned is that the best use of an operator's time and skill is to focus on printing and not become a measurement engineer. So in a real sense, which we learned about this aspect of our motivation only late in the game, we want to make viscosity measurement irrelevant to the flexo business. We want to make an automated system that's so reliable and so easy to use, and in the end, so invisible to the operator that viscosity no longer is part of the whole process. It just happens in the background, it happens automatically, and it keeps the color quality the best that it can possibly be. That's quite an ambition. We hope we're getting there. So what goes into an ideal viscosity control system? It's really got three components. There's the sensor, a device that measures the ink viscosity, and if you're running several colors, you need one for each channel, each color channel, and they have to be accurate, they have to be stable, and they have to be reproducible, which means that you can't have, for a really good system, you don't want a sensor that drifts, you don't want a sensor that needs repeated cleaning, and you don't want a sensor that needs repeated calibration. A perfect sensor should give the same values when it's new as it should when it's 25 years old. Then you need a controller. You need a system that takes the signal that comes out of your viscometer and translates that into a control algorithm that keeps that viscosity running at a constant level. And it's got to be autonomous. It can't require a lot of intervention from an operator. It has to be accurate, like the tighter the control, the better. And like the whole process, it's best if it's invisible. If you don't need to look at it, if you don't need to change any settings on it, it just runs and you don't even know it's there after a while. And then finally, and perhaps the most important, is the user interface. How does the operator interact with the whole system in such a way that they don't have to worry about the measurement principle? So the interface needs to be simple. You can't have to think about it a lot each time you want to make an adjustment. It has to be intuitive. You don't have to have the learning curve every time you need to change something in it. And like the whole system, it should be transparent. You should look through that user interface at color quality and not at viscosity. So we like to think that InkSight is that ideal system. It's based on 3 pillars, as we say. The first is our SRV inline viscometer, which I'll show you in a moment. The second is the controller, which we call a predictive tracking controller, because it follows the viscosity signal given out by the viscometer very closely and doses solvent that actually anticipates which direction things are going and how much solvent is going to be necessary. Actually, the minimal amount of solvent that it takes in order to correct the viscosity toward the value that we're looking for. And finally, our user interface, we call the color lock, because it enables the operator to select a color density based on test prints or by reloading a previous job, and then hit one button, and one button only, that locks the color density to viscosity and keeps it running at that level. So here's a look inside the InkSight system, as we call it. First of all, the InkSight is a multi-station ink viscosity control system. Means that it's modular and you can outfit as many or as few stations on your machine as you would like to. And then it's backed up by this control, the predictive tracking control, and it accepts the signal from the sensor, and it activates a solenoid valve or a pneumatic valve, depending on whether you're running water or solvent, and it doses just enough solvent into the ink bucket to correct for losses due to evaporation. And then, of course, the final component is your color lock interface, which I'll show you a bit more of later. This is essentially the same thing. I'm gonna move on to the next. Well, yeah, one of the niceties we've developed a handheld smartphone app where you can control the whole thing from your smartphone. You don't even have to stay glued to a console to understand what's going on in your process. So let's take a look at the SRV symmetric resonator viscometer. It's a patented system, have several patents on it, and we think it's the best of its class in the industry. It's extremely compact. You can install it anywhere. It's hermetically sealed. It's impossible for anything to get inside there and foul it. You get extremely repeatable measurements from it, and it's very responsive. It takes one measurement every 1.5 seconds, and it's completely uninfluenced by shocks or vibration, either from banging into it accidentally or from machine vibrations.
Joe, let me interrupt you for a second. We have a question that came in.
Yes.
The question that I told you was going to happen.
Sure.
They're asking, what about control of pH for water-based flexo inks?
Well, maybe I'm going to give an answer. Perhaps Bert can elaborate on that if necessary. But first of all, we know that water-based systems tend to be of much lower viscosity than the solvent-based systems. And our sensor is able to resolve those differences also. We have also installed systems where we have a pH probe that goes into the ink along with the SRV sensor. And we have a channel built into the software and the controller that enable measurement of pH and also dosing of the amine water that is necessary to correct the pH.
Great, thank you.
Okay. Bert, does that sound right? Bert, you're muted. Let's see. Bert, you're still muted. Let's see.
Well, we are using solvent-based inks and water-based adhesives. And with the water-based adhesives, you don't have to correct the pH, and the same for solvent-based inks. But as you told, pH can be controlled with the Rheonics system as well.
Okay, thanks. So this is my favorite picture. This is what the sensor looks like. It's only about 6 inches long and weighs about half a pound or so. And we like to think it's very photogenic. And as you can see, it's all composed of 316 stainless steel. It's hermetically sealed. And because the geometry is very, very simple, if for any reason, for instance, in the water-based system, or if you let your ink dry on it, you can just take a rag, a solvent saturated rag, and just wipe the thing off, pull it out, wipe it off, stick it back in, no recalibration necessary.
You know, Joe, there's another question that came in that's directly related to that. And the question is, how does the SRV sensor stay clean in water-based environments where the ink has a tendency to harden on and become nearly impossible to get off?
We have, that's a great question. First of all, the cleanliness of the geometry of the thing is very helpful in keeping it clean, because it keeps, we locate it in the press where you have a decent flow of recirculating ink. And the other thing is it has a self-checking feature. You can hit a button on the color lock interface, and the sensor will tell you if it's clean.
Oh.
So if you suspect that things are drifting, that it may be getting fouled, you can pull the sensor out, wipe it down, put it back in, and keep running.
Interesting. And then there's one other, just a follow-up question to the previous one. What do you control first, the pH or the viscosity?
That I cannot tell you. I don't have personal experience with that, Bert. I don't know if you've been in on some of this work with that Sunil has been doing.
Well, I can't give an answer as well. I don't have experience with pH control. Maybe can Sunil tell you? He's sitting next to you.
Sunil is unfortunately not sitting next to me. I thought he
okay.
would.
That's okay, Joe. What I'll do is I will give you these questions and with the email attached, and you guys can respond to the answer later.
Right? I know that Sunil is our CEO, and he's installed some of these systems on water-based machines, and he has firsthand experience with that. He was the chief designer of this whole InkSight system, so he will have an answer to that. Okay, so again, well, we talked about this, that the sensor never needs calibration or maintenance except for the occasional wipe down if it gets fouled. It's very easy to install. Here's 4 sensors installed on a windmiller press. And you can see they're just stuck in a pipe T in the ink line. And that's all it takes for installation. It's in contrast to some other systems, which are actually quite bulky and need special supports and installation hardware. And the sensors are extremely stable. We take sensors that have been in use in various industries for quite a while, and they haven't budged a bit in accuracy. So we anticipate that these things have at least a 25-year expected lifetime. Then here's the screen of the predictive controller. This is showing this color lock interface. And what's remarkable about this system is that it takes measurements every second and a half from the viscometer, and it will dose solvent as often as once every 20 seconds. And it'll decide what size of dose based on its previous corrections. And some of those doses can be as little as several milliliters. So this thing is really active. Your valve is going chick, then 20 seconds later, chick, and it gives you another dose of solvent. And as we'll show soon, the deviations are in viscosity are so small that expressing them in cup seconds is not very productive. We instead use centipoise or millipascal seconds to express viscosity, because it's a much finer ruler. You can see the it's like using a finer ruler to measure something that's very small. So what are some of the things that the InkSight corrects for? There's differences in initial viscosity and setup. You'll start your ink, for instance, somewhat thicker than you're accustomed to doing. And during a startup routine, then the controller will add sufficient solvent to get it at your target, and then allow you to make small corrections in order to get it to the final density before you start to print. It's also corrects for temperature changes, and we'll have a bit more to say about that a bit further down the line. Of course, the biggest challenge is evaporation. When you have an open doctor chamber, you're constantly losing solvent or water to the atmosphere, and the ink keeps thickening. So the controller will even out those kinds of variations. And also another challenge is when you, on a long run, when the ink starts running low in a bucket, and you throw in a big slug of fresh ink, then that's going to change the viscosity in the total ink system as it mixes in with the ink that's already in there. And as we'll see, the InkSight is very capable of compensating for even very large disturbances like a large dose of fresh ink in the bucket. So then here's the third part of the equation. It's your color lock interface. And here you see this has got 1, 2, 3, 4, 5, 6 active channels. Your ink colors are over here, and the way that this is used is when you're setting up your job and you are taking measurements of color, you're running some material, you're adding, letting the system add solvent. When your reading is within the tolerance that you are happy with, you just hit this lock button, and then your color is locked. You don't have to pay any more attention to the color unless for some reason further down the line you see that things are drifting and you want to make minor corrections. So here's a review of what here's what the color lock console looks like on the main control console of the windroller press. And here's the screen of we call the InkSight Smart View monitor. So you can have monitors anywhere in the system, but then at the console you'll have one major input monitor. So again, the advantages are operator independent measurement. It has nothing to do with how skillful the operator is in manipulating viscosity cups. It's a user-focused interface, and a further advantage is that if you are if you have a highly automated plant and you want to keep statistics and keep track of how much solvent you're using, things like this, then you can seamlessly integrate this system with your factory automation and data collection system. Okay, so for the last part of the presentation, we're going to show you some actual measurements and viscosity accuracy plots that were done at Bert's plant. So first of all, how is it used in setup? So the first thing we do is we say, okay, we're going to work on one particular channel first, one particular ink color. You click the auto button when the print is accepted to the master. You have sufficient agreement, and then it runs on its own. But you can set alarms, and if some kind of intervention is necessary, if for some reason the color, the viscosity or the color is drifting too far, you can set an alarm that will alert the operator that something needs to be done. Okay, let's take a look at how, let's go directly to here. Sorry, got a couple of extra slides in there. So here's the picture of where this thing, where these are two sensors installed on Bert's press. One of them is in the old style, just a pipe tee, and we also offer a sensor adapter, which is the correct size, correct threads, and goes directly in the ink line. And here's the InkSight controller installed on the press. And here's the ink system here. We have 8 buckets, 8 station PrimaFlex CS. And here's the color lock interface installed on the central control panel. So what happens? Start a job. First of all, you pre-mix the ink recipe, but you start with a somewhat higher viscosity than you're accustomed to using. And that leaves some headroom so the system can begin to dose solvent and thin it down to the actual working viscosity. Then as the setup progresses, of course, there are 2 possibilities. One is that you're setting up a new job, in which case you're going to have to pull some sample prints and keep comparing color density to your target. And then when that color is correct, then you lock the color lock button. Or you could be reloading a job that you've run before. And here's where the first major advantage of this system becomes apparent, because the sensors are so accurate and so repeatable that you can actually load the set points for viscosity from a previous job, and you very much shorten the whole setup procedure. It especially is good for reducing scrap during setup, and it almost completely eliminates trial and error matching of your color density. So here's what.
Joe, I'm going to interrupt you for one quick second. You had asked me to keep an eye on the timing for you. You got about 15 minutes left. Okay.
Okay, great. Okay.
Yep.
Thank you. So here's a plot that's taken from the console, and it shows the setup procedure. So here, the black line here is the measured viscosity, and this here is the initial viscosity target. And what we're going to try to do is we want the system to automatically dilute the ink until it reaches this set point, and then switch into the running mode from the startup mode. So here we see that the viscosity is rising, and here the viscosity control is switched on at this point. And we have something called a turbo mode, which allows the system to add larger than usual doses of solvent in order that we can get the solvent down to the viscosity down to the working level as fast as possible, so we can start running. So it starts off with a lower set point, but then the software recognizes when the the rapid change in viscosity is happening and when it's time to change the set point to the actual running level. So that happens over here, and bingo, the two things converge. And now you see that the InkSight takes over and starts adjusting it, the viscosity toward the desired set point. The vertical magenta lines here are doses of solvent, and you see how frequently they're happening. And also the length, the width of those bars shows you about how much relatively how much solvent is being added in each dose. So still during the setup procedure, the operator is taking samples and seeing how good the color match is, and the operator decides at this point it could use a little bit of a correction. So they then change the set point and again hit go. And here we get to the actual running control part of the algorithm, where the total deviation of ink viscosity, believe it or not, is limited to about plus or minus 1 centipoise, or roughly 0.2 of a cup second. And as you well know, if you've used cups, this is not only not possible to do with a cup, but you can't even resolve those kinds of viscosity differences using a cup. I think the most skilled operators can read a cup to about 1 second or so. So then during the actual print run, the InkSight system keeps the viscosity on its ideal point that you set during setup. And it'll keep that viscosity throughout the run, no matter how long the run is. So just to show you that, Bert furnished us with some data from a 24-kilometer run, which was started and restarted on each of 5 different days, and also at different press speeds, where we know that color density, that press speed is also one of the factors that influences color density. And here is the total color deviation for this one particular green color here, that over 5 days and 24 kilometers, and it has been constantly below DE 2000 factor of 2, and most of the time substantially lower than that. And the sense during all of these measurements, the sensor was never taken out of service. It was never taken out. It was never cleaned, and it was never recalibrated. Also, each time the run was continued, instead of going through the setup procedure each time, the operator was able to load the previous viscosity targets from the last run and just run without any additional setup to these kinds of accuracies. Now, what about when you add doses of fresh ink to the ink bucket? So this is where this is an event. This is an ink addition event, and here we see that the ink is added. Here you see the accuracy again, the control accuracy, this phenomenal control accuracy of less than 1/2 of a centipoise, or about 1/10 of a cup second. And then when the ink is added, we get a spike as the fresh ink begins to mix in with the ink in the system. Your viscosity rises by 3 centipoise, which is still less than 1 cup second, and then very quickly recovers its initial viscosity level to exactly the same set point as before that ink addition. So now I'm going to add a little bit of spice to it, and this again is thanks to Bert's research and his scientific curiosity, which is if you look at what viscosity does actually, how it contributes to the printing process. It actually contributes in two ways. One is, first of all, how does the ink flow when it hits the substrate? How does it flow when it's hitting the analox roller? How does it flow when it hits the plate? And how does it flow onto the substrate? So there, of course, viscosity plays a huge role because viscosity is about the fluid's resistance to flow. But then the second thing, which I was not aware of until Bert turned us onto this, is that viscosity is also a measure of the pigment loading of the ink. So the more pigment you have, given the same composition of the ink, the other components of it, the viscosity also rises. But then there's a fly in the ointment, which is that viscosity, in addition, is dependent on temperature. So it's kind of like some systems which cannot compensate for temperature differences are forced to use temperature-controlled ink systems. But this is a difficult thing to implement. It's expensive and hard to implement on an existing press. But we have worked out together with Bert a series of formulas where you can actually compensate the measured viscosity for factors like temperature and the dependence of viscosity on the ink pigment content, and come up with what we call a temperature compensated viscosity. And then, of course, you can get the Inkside system to run to a constant temperature compensated viscosity. So you get a double effect. One is that the flow properties are kept constant, and also it's an additional factor for stabilizing the pigment concentration in the ink. And here's a sample of a run done with temperature compensated viscosity. Here we see the light green trace is temperature rising by, well, not very much. The temperature is on the right-hand side here. It's about half a degree Celsius, or a little less than half a degree Celsius, or about 1 degree Fahrenheit. And yet the viscosity is constant to within about 1/10 of a centipoise or so. Okay, so for a last thing, I promised that I would say something about the kinds of solvent economies that are possible with the InkSight system. And here's, again, thanks to Bert, he's been tracking his solvent consumption before and after he installed InkSight on his press. And let's see, something, here we go. So previous to 2017, his solvent consumption was on the order of 28 kilograms a year. And that was like fairly constant for the last 3 years. And then after he began using first on one press and then on a second press using InkSight, he was able to bring his solvent consumption down to about 16 kilograms a year. And the total emissions were brought down by almost a half, to a half. And here he has the trends graphically shown of how the solvent consumption ran before and after, and also the emissions. So to recap, here are some of the key user benefits from InkSight. One is, first of all, it places the focus on print quality instead of measurement skills. The operator can concentrate on what they do best, which is making the best possible prints with the available equipment and the skill set that they bring to to their artisanship. Secondly, it brings substantial reductions in setup time and therefore of scrap, and especially setup time when you're reloading existing jobs. One of the advantages of flexography is the agility, how quickly you can change over from one job to another, and InkSight supports that by making the setup process a lot faster and less painful. Then, as we said, color quality is supported even over the longest runs, and it radically shortens the setup time, as we just said, and also this reduction in solvent and consumption. And I think another key benefit is that it really reduces customer dissatisfaction with inconsistent runs. That the more satisfied your customer is with the quality throughout the length of the run, the better positioned you are to keep that customer as a valued partner and to get repeat business from them. Okay, that's it from our side. Again, thanks a lot to Joe and to Mark, and particularly to Bert, who has really supported this project right from the beginning.
Yeah, and thank you, Joel. We really appreciate you taking the time and presenting this for our members. Very informational. And I just want to thank everybody else out there for coming. And I want to let everyone know that we do have another Membernar scheduled for November. We're skipping October because we'll all be at Fall Conference in Frisco, Texas. But November 4th, mark your calendars. Mark Samworth from ESCO will be presenting an extended version of his Fall Conference presentation. So that registration is not live yet, but will be live in the next week or so. So thank you again, Joe, and everybody at Rheonics, and everybody have a terrific day.
Thank you.
Take care. Bye-bye.
Bye.